All right. Well, good morning, and yeah, happy Thursday. So I sent out an announcement, but I'm traveling this weekend I'm heading over to Duke University. So I'm like after this class, I have a flight to catch at 1 o'clock, flying over to North Carolina, and I'll be attending a conference for R. So I'll learn more. I don't know. There's all kinds of stuff happening in the world of data science and R and Python and whatnot. So I try to attend conferences. I went to the Python conference earlier this year, and now I'm going to the R conference. And anyway, looking forward to it. But anyway, that just means no office hours today, and then I'm going to kind of shift things around. So I will have office hours on Friday, and I will have office hours on Saturday, but they'll both be, I guess, at 4 o'clock, which would be, I think, 7 p.m. over there. And so, maybe I'll be eating dinner or something. but yes, we'll have that. And then, yes, we still have class today, and then I'll be back Monday. So class will resume on Tuesday. No problem. Okay. In the modules, I think, so I'm still kind of working on finding the exact data sets and stuff, but I posted a little bit of information about our competitions, okay, the Kaggle competitions. This is basically your final project. So there's no final exam for the class. You just have these final projects, and one's going to be a classification project, and the other is going to be a regression project, okay? And they're going to be hosted on Kaggle, and I'll explain how all of this works. But you'll do this in teams, okay? And what's going to happen is on Kaggle, I will post the data, and you will have training data and test data as well. So the way the training data works is you'll have all of the input variables X as well as the output variable Y. That's going to be the case for the training data, okay? And then for the test data, you will have all of the input variables X, but I will not give you the output values of Y, okay? But I do have the output values of Y, and those are secret. Those are hidden from you, okay? And then so you create a model based on the training data. And then once you have your model based on the training data and you're like, okay, I'm able to make good predictions for these values over here on Y, then you run your test data, the test values through your training, through the model. The model then produces some outputs, okay, predictions for Y. You upload your predictions, and then Kaggle takes your predictions, compares them to the actual values that I've secretly uploaded to Kaggle, compares them, and it gives you a score, right? And this is what it's going to do for everybody's, all the different groups. And then you'll be ranked based on how well your model makes predictions on the test data. So basically, some points of it, a part of the competition performance, if your team doesn't perform super great or whatever, you might lose a couple points here, and then if your team performs really well, you'll earn some extra credit points and things like that. I think I'm not 100% sure how many groups we'll have. I think we'll have less than 18 groups, but yeah, but anyway, this is going to be kind of how it goes. You'll also have to submit an R script that works, okay? So you'll submit that, and I'll kind of verify that your thing works and makes predictions, and then you'll submit a report talking about the model and how you found it and created it and whatnot, okay? So that is, and so as the course goes on, I'll talk a little bit more about the final projects themselves. I'll talk about, so once I have the data sets picked out and finalized and to get them into competition form, there's a decent amount of cleanup that I have to do to kind of make sure it's compatible with the way Kaggle evaluates things. So I'm working on that, and I will share and post that to you guys. Meanwhile, there is I think this works. Maybe somebody can verify. I've created a sheet in Google Sheets. It should look like this. Okay, it looks like somebody managed to log in and access it. Okay, and it just has the names of everybody enrolled in the class. And so, fill out this information, and perhaps you want to talk to some of your neighbors or whatever, I don't know, that are physically present in the class and whatnot, and you can say, hey, do you want to work together? And you can say, I found a group, or I guess maybe I've not yet, maybe one of the possible things is like, I've not yet found a group, but I plan on working with, I don't know, who's, Julio Frank, right? Or who, someone else in the class, and you can kind of list that information there. Okay. And anyway, so put in, your availability and things like that, because that's going to be important as far as trying to work together with your group and stuff. Okay. All right. I think, any questions about that? So, okay. All right. Looks like it's working, because I see a lot of people logging in. Okay. So that's good. So that, I should make a deadline for getting into a group. Probably by the end of the second week or beginning of third week. I don't know. We'll give you, maybe beginning of third week or something. I'll give you another week and a half, 2 weeks to find a group. Okay. So that's that. All right. Let's go ahead and take a look at our lecture for today. Okay. So I'm going to. I should talk. Actually, I need to finish just a little bit from our first lecture. Is there not a quiz published for today? Yeah, quiz lecture 1-2, right? So, huh? Oh, this is due today, so you should. This is lecture 1-1. This is just do it at home. It's like a homework quiz, so it's not in class. When's it due? Okay, here I'll extend the time. If you didn't do it, you have until the end of today. Let me extend the time to, I guess, 11. The last time I can pick, I guess I can type in 11:59. But we have until the end of today to finish this. But in general, as far as these quizzes go, just take them before the next lecture. Okay. Let's see. So I wanted to finish something here. So just a little bit about tidy models. So this is going to be the package that we're going to be working with for our course. And again, as far as fitting statistical models, I would say you have, Python and R are both popular choices. As far, in industry, probably Python is a little bit more popular for just because a lot of kind of more high-powered neural network type stuff flows maybe a little bit better through Python. and so that is, and that seems to be the direction that a lot of things are moving in. But as far as fitting just a bunch of different generalized models, I think a lot of models, like when researchers and people, create new algorithms and new models and things like that, they often publish R packages first. And Tidy Models integrates really well with a lot of new R packages and things like that. So I think they're still very useful. I might supplement. I don't know. It's kind of a lot of work, and show like how to do similar operations in, say, scikit-learn in Python or something like that. But anyway, I am a big fan of Tidy Models. I think it does create kind of this very nice and streamlined interface for you to interact with your data and form established statistical models and test them out and evaluate their performance and compare a whole bunch of different models and do tweaks and things like that, which are all kind of practical considerations that you have to do as you fit things. Okay. So anyway, so regarding Tidy Models, you'll get this installed using install.packages Tidy Models. This runs on top of the Tidyverse. I'm assuming everybody's kind of already a little bit familiar with the Tidyverse, and if you're not, that's like part of your first homework assignment. Is did everybody get a data camp invitation? You should have. Okay. And hopefully you can access it and whatnot. If you run into a problem where it's like this link is not valid or something like that, that's most likely because you either have an account or tried to create an account with an email address that was different from the one that was invited. So I used whatever's on my UCLA. Those are the email addresses that got invited. And so the thing on my UCLA is Joe Bruin at ucla.edu, okay? And perhaps you're logged in with Joe Bruin at Gmail, okay? Or you created an account on DataCamp with Joe Bruin at Gmail. It's gonna say this link is not valid and you won't be able to get the premium access. So what you'll have to do is you'll have to log out and then create a new account with the exact same address, Joe Bruin at ucla.edu. Click that link, accept the invitation, and everything should work. Okay, and it's very like the address has to match exactly. So if you try to create an account with Joe Bruin at g.ucla.edu, it's going to say the link is not valid. Okay, so make sure you use the exact address there. So anyway, that's DataCamp, and your first assignment is to just kind of do the introduction to the Tidyverse, and then Tidy Models kinds of builds off of that. And then, so Tidy Models, we'll go to Tidy Models. So you can go to tidymodels.org, and Tidy Models itself. So the Tidyverse is a collection of packages, things like dplyr and ggplot and Tibble and things like that. And Tidy Models is also a collection of packages, and they all kind of work together. And each of these packages, does a different thing. And so the different packages within Tidy Models are RSample, Parsnip, Recipes, Workflows, Tune, Yardstick, Broom, Dials. I think there might be a few more. Okay, but so Tidy Models is kind of the package that you load, and then when you call library Tidy Models, it's going to load up all of these other packages. Okay, and so RSample is all designed about creating splits of your data between your training set and your testing set. And if you want to do like k-fold cross-validation, it's going to RSample does that, and we'll talk about cross-validation today. Okay. And then Parsnip is this package that integrates with other packages and libraries in R. And so I don't know if you've ever tried using different like machine learning packages on your own in R. There's like a whole bunch out there. Okay, there's like Random Forest. Okay, and then there's another Random Forest package called Ranger, and then there's another package that does like I don't know, E1071 I think does things like support vector machines, and all of these. So one of the great things about R is that it's actually really easy to produce a package and get it published into R and the CRAN library, and you can download it. Okay, but the downside of that is that everybody who publishes a package kind of has like different notation, right? It's kind of like when you pick up a math textbook, okay, and you go to the bookstore and you have different math textbooks. They all have slightly different notation, and you got to like spend like a good hour just kind of like getting used to someone else's notation before you can start reading through it. And the same kind of issue exists in R with all of these different packages out there. They all have like slightly different notation, and one requires your data to be formatted in a certain way, and others and they have different kinds of things. And so what Parsnip does is it says, hey, just learn kind of the language of Parsnip, okay, the style and the vocabulary of Parsnip as far as like how do you define your models, and then Parsnip under the hood will translate that into whatever package is out there, okay? And so there's a whole, like, not a whole bunch of people, but basically, some people's kind of jobs are to look at what are the new packages coming out, how do I interact with that package? They learn how to translate Parsnip commands into the commands for that package, and then that way you as a user only have to learn how to do things in Parsnip, and Parsnip will automatically translate everything to whatever package is out there. So it's really great because that can be one of the frustrating aspects of like, oh, a new package was just released. Oh, but I have no idea how to use it. And with Parsnip, you don't actually have to bother learning the details of that particular notation. Okay. There is a lot of times when you fit data, you have to do a bunch of pre-processing, okay? And that's what recipes are for. So pre-processing is things like, oh, you have a categorical column of categorical data, and you have to turn things into like dummy variables, right? Because all of our packages require things to be numbers. And so, dummy variables, you turn things into zeros and ones and things like that. Other things like you're missing data. So do we get rid of those? Do we fill in missing values? Do we try to guess what those missing values are? Stuff like that, what if you want to remove outliers, okay? Recipes does all of those kind of pre-processing steps, okay? Workflows will kind of combine your pre-processing steps along with different models, okay? So you can say, hey, sometimes I want to just throw away my outliers, okay? And sometimes I want to keep the outliers, and sometimes I want to just like cap the outliers. So like maybe your outliers are like 1 million and you're just gonna dial them all down to say like 100,000, like we're gonna just create like a ceiling value or something like that, right? And so you have like, and you want to know like, okay, how does this affect the model that I fit, right? So you might say like, okay, what kind of models do I get if I include the outliers? What kind of model do I get when I throw out the outliers? What kind of model do I get if I set a ceiling value for the outliers, right? So you have these different pre-processing options, okay? And then you might also say like, okay, well, I want to fit a linear model. I want to fit a polynomial model. I want to fit some other kind of model, right? And And the old-fashioned way is you'd have to like create a whole bunch of different scripts. You need to say, okay, here's the script where we're going to throw away the outliers and I'm going to mix it in with the linear model. Here's another script where I throw away the outliers and I do it with a quadratic thing, okay? All right, here's another model where I create a ceiling value for the outliers and do it with the linear model, right? With workflows, you kind of just say, hey, take this pre-processing recipe, combine it with this model, and you just kind of link them together. You don't have to write entirely new scripts, right? So you have these workflows. You can create things called workflow sets of these different kind of combinations. And it just makes things a lot more efficient rather than you having to kind of manually keep track of all of these different steps, okay? Tune is allows these kind of adjusting of the hyperparameters. It pairs well, it uses another package called dials. And so, as we introduce more and more different models, things like k nearest neighbors, you have this hyperparameter k. Like, do I use the 3 nearest neighbors? Do I use the 5 nearest neighbors? The 12 nearest neighbors, okay? That's considered a hyperparameter. And, which one do you use, okay? Other hyperparameters are things like in a random forest, how many trees am I going to go? How deep is the tree, each tree going to be, right? So these are all kind of different things. Okay, so anyway, all to say, you have a whole bunch of different packages. Each one specializes in some different aspect of modeling. Yes?
What are parameter grids?
Parameter grids? Yeah. So let's say, in a random forest, perhaps, and I haven't even talked about random forest, but one is like you can change how deep each tree goes, right? So you can have like a tree of 3 levels. You can have a tree of 5 levels, okay? So that's one of your parameters. And then another parameter could be, so in random forest, you have like how many variable choices to select from. And you might say like, okay, when you make a split, consider 5 variables. And someone else say, you know what, when you make a split, consider 10 variables, right? And all of these things are kind of like, on one side, if you have too many, it's going to be high variance, low bias. Okay, and on the other side, if you have too few, you'll have like, what did I say? You'll have low variance, high bias type of thing, right? And so all of these are kind of like, you have these different dials, okay? So I don't know, like if you have like these, imagine this giant like sound mixing board, right? Or like you're a DJ and you have these different knobs that you can tweak. And one is like, we want more, high variance, low bias, or in the others, you want the other side, you want low variance, high bias, right? And you have all of these different things. And so anyway, with the random forest, let's just say 2 of these parameters that you're messing around with is your tree depth, okay? And then the other is basically your variable selection, okay? And so the old-fashioned way without tidy models is you'd have to create separate scripts. And you'd say, okay, let's try 3 and 3. Let's try 3 and 5. Let's try 5 and 3. Let's try 5 and 5, or something like that, okay? And where do I have it? Do I have it somewhere in here? The parameter grid, where did you see that? Oh, right here, parameter grids, okay? Parameter grids will automatically set that up for you, where it's going to just say, okay, what are the choices you want for tree depth? Oh, 3, 5, 7, okay. What are the choices you want for variable selection? Oh, 5, 10, and 20, okay. And then it's automatically going to set up basically all of those combinations for you and say, all right, we're going to try 3 and whatever, 5, and 5 and 5. And I forgot what numbers they said, but it's going to basically create the grid of all of the different things. And, you could do it with, it grows, exponentially. Like if you have like 7 of these different dials that you want to change around with, it will create like the whole kind of array of every single kind of possible combination that you want to do. And so it's just kind of like an efficient way to set up all of the different combinations for you to try out all of these things, right? So again, as you're like kind of dialing in any of these things, it's like, okay, if I adjust this a little bit higher, maybe I have to turn this one down, or and it tries out all of these things for you. So that's what dials and tune kind of dials is like the the dials themselves, and then tune is kind of like these automated process instructions and stuff. Okay, yardstick measures how well your performance is. So it has all of the kind of different metrics of, root mean squared error and like F score and things like that. Okay, and then Broom allows you to kind of take these outputs and it puts everything in nice little tables, so you can kind of like treat the outputs of each of these models and these evaluations as tables themselves, where you can do statistical analysis and things like that. So, okay, so those are just the different packages within Tidy Models. I don't expect you to memorize all of these things, but these are just as I'm going through and teaching and covering all of these things, I'll say like, okay, and then in this package, we're blah, 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 right? Just so just like when you hear parsnip, you're like, no, what are you talking about? So, so the people of R, we're like I shouldn't say we, but like, it's a little bit of an eccentric group. And so like, why is it called parsnip? It's because a long time ago, there was a package called Caret, like the little, that symbol, okay? But I guess it kind of sounds like the vegetable carrot, and parsnip does kind of like something similar to that package. And, parsnips are also like these vegetables that look kind of like carrots and stuff. There's just a bunch of kind of silliness going on with these naming things, okay? And so you'll learn a lot of stuff about this in the different textbooks. So yes, read the textbooks. And so yeah, this is blah 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 blah. Okay, but yeah, we'll take a look. Let's see. Anything else? What else did I have to say? Whoops, that's not what I wanted to click. Okay, and then data camp. All right, so introduction to the Tidyverse. All right, yeah, these are, once you accept my invitation to Data Camp, you have access to all of Data Camp, which is like a really nice thing, because if you don't have, like, if you didn't get an invitation from me, I think it's like $30 a month or something. 45? Oh, okay. Yeah. So it's expensive. And I think you get, I want to say 180 days of access or something. So even after the class ends, you can continue like learning and doing stuff. And they have stuff in R and Python and SQL and, other things. So I will just assign a few chapters. And then, if you want, keep learning, and then you get like little certificates of completion and stuff. And overall, I have to say their content's very good. I'm quite pleased, and so I would happily recommend their product. That even if you have to pay, I guess $45 is a lot, but if you make good use of it, right? It's kind of like a gym membership. If you make good use of it, it's very well worth it. But if you like pay for it and you don't use it at all, it's a waste, right? So, okay. All right, let's keep going. So in tidy modeling with R, there's going to be this data set that we use throughout to kind of illustrate a lot of these points. And this is the Ames housing data set. Are you guys already familiar with this? Have you guys used this in other classes? The Ames housing data set? No? Okay. It's a popular data set. It's already, 15 years old now. It came out, I don't know, maybe not quite 15, but it collected housing data from Ames, Iowa, so Ames is like a city in Iowa. There's is that Iowa University of Iowa somewhere. It's basically a college town, and they got housing prices, okay? and housing characteristics. And so there's a whole bunch of variables that include things like the number of bedrooms and how big is the garage and does it have a fireplace and what neighborhood is it in and what's the lot and the condition and the price. And the authors have already done a lot of cleanup of the data. When you look at the prices, it's gonna things have changed quite a bit in the housing market in the last 10, 15 years, already. So the housings feel, the price data feels outdated, or it is outdated, but it still is a useful data set as far as doing some analysis here, okay? And so if you load it up, okay, so we can get the data by calling library model data. So here I have R, and I've started this up. I got to update my R. The latest version of R, I think, is 4.5.1, and I have it on my home computer, but then my laptop doesn't get as much love, so I have to do all the updates here. I've already loaded. I've already run the commands library tidyverse and library tidy models. So is this big enough? Can you guys read that? Should I make it bigger? Those in the back? We're okay? Or okay, all right. So I've already run library tidyverse and library tidy models. And so now I'm gonna do library model data, okay? And if you get some kind of error that says that package wasn't found, just do install.packages, and then you put in quotes, whatever library you need, okay? Or you can come over here to this tab where it says packages, all right? And then it's loading, and you can either do install, or you can search for something like tidyverse, and then let me see. I'll click update. Oh, look, all of these things need updating. Okay. So, tidy models can be updated to 1.3. All right, so I'll go ahead and I'll do that. All right, so I'll go ahead and I'll update tidy models. See, it's warning, cannot remove this. Okay, yeah. All right, if you see successfully unpacked and MD5 sums checked, those are all good signs. And it looks like it worked. All right, so I'm gonna do library tidyverse. And that looks like it worked. And then we'll do library tidy models. Oh, package or names in load name. What happened here? CLI is already loaded 3.6, but 3.6.4 is required. Okay. All right. So sometimes you run into errors. So we will, I'm going to do session, and we're going to quit our session. Oh, I guess it just quits RStudio completely. All right. Let's try updating this. It might tell me, let me see if I can do this. All right. So library tidyverse. Might tell me I need to update my R. Let's see. So that worked. Okay, library tidy models. All right, so let me see. All right. I'm going to do install.packages CLI. Let's see. Do I want to update? Sure. Restarting. One or more of the packages are restarting R is highly DS. I thought I said that. All right, so sometimes we run into this issue. All right. Warning, cannot remove prior install. Permission denied. Okay. Sometimes we run into problems. Okay. Well, this is how so I'm going to just look for R directly. R in I think I'm 443, right? So I'm going to right click this. I'm going to do run as administrator. And then I'm going to try installing it here. So well, this is, okay, so I'm going to do install.packages. Sorry, the text is super small here, but I'm going to write install.packages CLI here, and hopefully it will run. Pick somewhere in the USA under old-fashioned R. It looks like it downloaded. I don't know. Okay, library CLI. Did that look? Okay, so, all right. We'll try that. So that seemed to work. Save workspace image. Now we start RStudio up again. All right, let's see if this will work. Here, let me try library CLI. Seems okay. All right, library tidy versus the risks of doing things live. Okay, tidy models. Okay, no errors this time. All right, so success. So sometimes that happens. If you're trying to install a package in RStudio and you keep getting this loop of like, you need to restart your R session, and you're like, yes, do it. And then it says, you need to restart your R session, and I can't do it. And then sometimes you have to quit RStudio, open up regular old plain R, and then install the package there. And then if you need to, you can run as administrator, and sometimes that clears up the issue. But all right, it looks like we're okay. So I'm gonna now do library model data, which is what we want. And then we load up the Ames data by typing in data Ames, okay? So most of the time, we load up data by like importing a CSV file, okay? So, but in this case, this is one of those data sets that are built into a package, which makes it nice. And then so as soon as I call data Ames, it loads up Ames into the environment. And I can click it, and I can see what it is, and we can see it's a Tibble, 2,930 rows, 74 columns. I can also ask, what are the dimension of the Ames data? And it says 2,930 rows, 74 columns, and this is what it looks like. If I click this, I think if I click this button, I get kind of like the spreadsheet viewer, and you can see just some of the different columns. MS subclass, 1-story 1946 and newer, all styles, 2-story 1946 and all, okay, in residential, low density, lot frontage, lot area, street, alley, lot shape, land contour, et cetera, et cetera, et cetera. All kinds of stuff about the house, right? All right, we can take a look at the histogram just to kind of get a sense of variable characteristics. It's good to just kind of look at a, let's say like a histogram or the distribution. So here I'm going to, I create a histogram of sale price. And for this, I just did ggplot, Ames, and geom histogram, okay? So I hope this is okay. This is just basically making a histogram. And what we have is, how would we describe the distribution of this data? We would say it's unimodal and skewed what? Skewed right, okay? And basically anytime you have, like if your variable is money, something financial, almost always it's gonna be skewed right, because you know, in our data set, it looks like most of the houses are, you know, 2E05, so that's 2 followed by 5 zeros, so $200,000. Okay, so I mean, again, 2010, Ames, Iowa, you know, like in Los Angeles, what your average house is like $900,000 or something like that. Median price of a home is something crazy, and I don't know, but anyway, so in Ames, Iowa, it looks like median price is probably like $150,000, and a lot of houses are somewhere between $100,000 and $200,000. And sure, some houses go up to $400,000, and then you have, I think the maximum value, there's like a tiny little line, and you might not even be able to see it, is like $700 something thousand. Okay, So that's like the mansion in Ames, Iowa, in our data set. And that's anytime there's something financial, you're going to have something very right skewed. Vast majority of people probably make somewhere between, I don't know, $30,000 and $200,000 a year as far as income goes, and that's going to cover 90-something% of people. But then, are there people who make like $1 million or $5 million a year? Yes, that exists, and that's $1 million is $200,000. As much money as that sounds, is a lot closer to zero than it is to $1 million. Okay, and it's way closer to zero than it is to like 5 million. Okay, 5 million is 4.8 million away from 200,000. So you're gonna have these things that are very right skewed. Okay, any kind of product like cars, right? Most cars probably like $30,000, $50,000, something around there. Are there cars that sell for $100,000, $200,000, $300,000? Yeah, you can buy a Lamborghini or Ferrari or things like that are cost more than a lot of people's houses and stuff. And so you're gonna have this very kind of right skewed because that top echelon of income earners and stuff. I don't know, they're like in a different zone. But anyway, this is what we have. This is what our histogram looks like. And so when dealing with something that's very right skewed, we might want to transform our data, okay? Especially if your metric for error, right? So how are you evaluating your model? If you're using something like basically a lot of these things are going to be something like mean squared error, root mean squared error. Anytime you see that word squared, what is the property of having squared errors? Okay, squared errors penalize big errors a lot more than small errors. Okay, versus just sum of errors, you don't penalize. You penalize all of the errors equally. So just to illustrate, is it better to have 10 errors of size 1 or 1 error of size 10? Okay. If you're doing absolute values, sum of absolute values, those are exactly the same, right? 10 errors of 1 adds up to 10. 1 error of 10 adds up to 10, okay? But if you're doing squared errors, okay, 10 errors of 1, you're going to do 1 squared times 10, you get 10, okay? 1 error of size 10, 10 squared is 100, okay? So the squared error will say it's way worse to have 1 error of size 10 than it is to have 10 errors of size 1. Okay, and we often use squared errors as our measure of performance because we're saying, we really want to avoid having huge amounts of error because those might be the ones that like cost you the most, right? Like if you're like running an insurance business or something like that, right? Any kind of financial thing, making one mistake of like $1 million or something could kind of like break you at that time, especially if it comes in all at once or something. So you might penalize squared errors. What ends up happening then is that your model is really, really, really heavily influenced by those outliers. Okay, and so when you took 101A, your linear regression course, you probably learned that, right? These outliers have a lot of influence, right? You have like Cook's distance and leverage and things like that to kind of illustrate how much influence these outliers can have. So you can kind of, reduce that by doing some kind of transformation. And you have different options for transforming them. A simple method is to take the log, right? So if we just do log base 10 or log base E or something, this is what ends up happening. So all of our so if we take the log of all of the prices, this ends up being the distribution, and we can try fitting that. Okay, so after doing a log transformation on the sale price, this is what we end up doing. Okay, and so that's what they do in the Ames housing data. Okay, so as far as tidy models go, for the rest of the analysis, they take the sale price, they're going to take the log of the sale price, and they replace the sale price column with that. So this is using the tidyverse language, dplyr. We're going to take the Ames data set, we're going to transform or mutate one of the columns by taking the log of the sale price, replacing sale price with that log price, and then we store it back into Ames, and this is going to transform the data. And so I'm just kind of following along with what they've done in the textbook where they've done this. Okay, and then the next thing, another thing that we can take a look at is these are just some other. I don't have these images in our slide deck, but as you read the textbook, this is a map. They've drawn a map of Ames, Iowa, and they've plotted all of the different neighborhoods. So I don't know if I can show you this. So they got some kind of map data, and then they've colored all of the different neighborhoods, and so and it looks mostly correct, right? So it looks like, okay, yeah, that looks like a neighborhood, that looks like a neighborhood, and but there are a few kind of plots that seem a little bit strange, like maybe classified incorrectly or something. But let's see. A few noticeable patterns. There's a void in the center of Ames. Okay, so this part right here, this is the university. All right. So that's okay. Iowa State University, and some a lot of the neighborhoods are like, this is like a big residential area, and you have different neighborhoods here, and they're all right next to each other. But this neighborhood is all kind of off on its own, right? Is what it's kind of pointing out. And then within the data set, there's also kind of this zone down here. This neighborhood is like isolated, and then within that neighborhood, there's also like, I don't know, almost like a little gated community within this thing or something. I don't know what it is, but like kind of its own thing. And, if you're not from Ames, Iowa, it's like, that's weird. All right. But, if you live in the town, you'd be like, oh, yeah, Meadow Village or whatever it's called. That's like, there's, Meadow Village within the Mitchell neighborhood, right? And so, if this were like a real data set, I mean, it is a real data set, but if you were truly curious, you might want to go into like Zillow, right? And you'll look at Ames, Iowa, and then you'll look up Mitchell, Mitchell neighborhood. Kate Mitchell Ames, I don't know, what is this? Is that the, that's the, oh, okay, that's the neighborhood. Yeah. That's the person's name. And is this the, that's her particular home? No, this is, it's an elementary school called Kate Mitchell. Yeah, it's in, I think this is, yeah, no, this is the part of the neighborhood. Yeah, right there. That's it. Okay. Well, but then Kate Mitchell Elementary School. Yeah, we can remove this boundary, and this is a bunch of stuff. Campus Town, and then what's the other? What was it called? It was called Meadow Village. That's right. Let's see, Meadow Village, Ames, Iowa. It doesn't like it. All right, let's try this. Zillow, Ames, Iowa. Okay, Meadow Village. Is that still a thing? Meadow Lane Mobile Park. Oh, maybe that's what it is. I don't know. No, can't find anything. Meadow Lane. Okay, well, anytime you're unfamiliar with something, having just some like local insight, right? If somebody's like, oh yeah, that's the mobile home park or something, like you can go like, okay, well that's going to help explain some of our things, or it could be something, right? And so anyway, all of this stuff is just kind of pointing out some of the interesting kind of things where it's saying like, you know what, we have the Somerset and the Northridge villages, or I mean neighborhoods, but it looks like maybe some of these things are classified incorrectly, right? Like this home looks like if I drew a line, I would say, okay, over here is Northridge and over here is Somerset, and but it looks like this dot got labeled wrong, and maybe these ones got labeled wrong. Anyway, yeah. If you are writing a fictional story and you want to make up a fictional town, just name someplace like Northridge, East. Just take north, south, east, or west, and then take some kind of geographic feature. So like Northridge, east like Westwood, East Gate, or South Gate, South Bay, and you'll like come up with all kinds of random like this is how we just named all of America. Just take some cardinal direct, North Park, I don't know, whatever, South Meadow, whatever you get, okay? And you'll get these things. All right, so it's just kind of pointing out all of these things, and that's what it says. And the reason why the book spends so much time all of these neighborhoods, because, well, one, neighborhoods influence prices quite a bit, and you want to have some insight into your data. And so it's just trying to get you familiar. It's kind of just like, oh, you don't know anything about baseball. This is just a little bit about baseball so you can understand some of the data, right? You don't know anything about Ames. Here's a little bit of information about this, right? So, if you were looking at housing prices around UCLA and stuff, you'd say, yeah, okay, Westwood, there's a whole bunch of apartments near the campus, and then the houses are like super nice, and, Beverly Hills is like a really nice area and whatever, okay? All right, the next part, chapter 5, is called Spending Our Data, and it's about like kind of splitting your data into, training and testing and things like that, right? And so, as you think about the job that we have to do, okay, as far as fitting our model and then making good predictions and things like that, one is we have to estimate the parameters. That's going to be fitting the model, okay? And we're going to have several competing models, right? Because we're going to have to say like, okay, is it better to, treat the outliers this way or this way? Is it better to fit a linear model or this kind of model or some other kind of model, right? And then you say like, okay, this one looks promising, so let's start to fine tune it, okay? And how do you know if you're doing a good job? You have to measure its performance. So there's all kinds of stuff that has to go on, and all of these things require data, okay? In some of these tasks, you want to use different data as far as, especially something like assessing performance, you want different data, right? It's just the same kind of way, like if you're going to evaluate someone, like how well did they learn the subject, okay? You don't want to give them a practice test and then ask the same questions from the practice test, because then you can't really tell, like, did you just memorize ABCD from the practice test? And so you can answer ABCD and get 100% on the exam because I'm using the exact same questions. Or like, did you just memorize the answers from the practice test? That's not going to be good. And the same kind of problem can happen when you're training and fitting a model, or training and fitting a model and then testing it. If you're using the same like data set on the training as you do during your evaluation phase, it's hard to know, like, did the model just kind of memorize all of the answers and is just regurgitating everything, and so it's doing well? If I gave you new questions, like, will you still kind of perform well? And so, if you're a teacher and you're writing an exam for a class, you want your kind of practice questions to be similar, but not totally different from the exam, okay? Because like if my practice test is very different from the actual exam, like everyone's gonna be like angry, and And it's not going to be like, what was the point of giving you the practice exam if the actual exam is nothing like it, right? But at the same time, you don't want it exactly the same, okay? And so you want to kind of, and so ideally you want your kind of training set and your test set to be like of a similar quote feel, but not exactly the same, that hopefully generalizes to the broader population, okay? So, how do we split our data for the different tasks? That's what we want to do, okay? And so kind of the most common approach that we're going to do is we're going to split our data into a training set and a test set. The training set usually is a larger portion of our data. A lot of times we do like an 80%, 20% split between training, 80% 80% training, 20% testing, but you can do 70, 30. I mean, you could do 50, 50, things like that. And the training data is all used for estimating your parameters and engineering features. Engineering features is just a fancy way of saying like messing around with your variables to possibly make new variables or transforming your variables or things like that, okay? Trying out different models, okay? And then that test set is kept secret apart from kind of the model development process. Again, as if you're teaching a class and you want to do it, I can give you the practice exam, and I would have to keep the final exam a secret. We don't want the students to see the final exam before it's actually time for exam time, because again, if somebody sees it, then it's like, oh, did you just memorize the answers on the final exam, or did you actually learn the material, right? And that's you want to keep that part separate from the model fitting and training process, because if you start incorporating the test set, then it's like, well, is the model just memorizing the test set, right? So it's used at the end. Usually it's kind of like we have a few candidate models. We have like 2 models that we really like. Which one's going to perform better? And you test them out on the test set. And maybe the performance is the same or like similar, and so it's really hard to choose. Maybe something gets differentiated at that point, and that's what you have, right? If you kind of keep going back to it, right? If you look at the test set again and again, then it becomes part of the modeling process, and you're no longer sure if you're doing this. Okay, so tidy models makes this process really easy. If you didn't have tidy models, I guess back in the day, back when I was in school and I had to do training and tests, it's like you would have to write a script where you would, create, like if you have 2,930 observations, you'd probably create a vector of 1 through 2,930, and then you'd call R sample or just sample to randomly select some of those rows to be part of your training set, and then you'd pick the complement to be part of your test set, and you do this, and it wasn't terrible, but it could get tedious, and it was easy to make a mistake. And so tidy models makes this nice for us by giving us this function, okay, and this is going to be called initial split, and the output of this is a little bit cryptic, okay. When you take the original Ames data, I'm going to run it through initial split. It produces this object called Ames, whatever it is. I'm calling the resulting object. I'm storing it at Ames split, okay? And within Ames split, it says we've done a total of 2,930 rows, and 2,344 go in the training, and 586 go in the testing set. And basically, it has taken the Ames data and it has kind of put little indexes and says these rows belong to the training set, these rows belong to the testing set, okay? And then from there, you can extract out the training set and you can extract out the test set separately, all right? And so you can say, I want to extract out the training set, I want to extract out the test set, and you can do this, right? And there's other functions that just take this entire split and does some kind of operation on it directly, okay? But you can extract out the different portions, right? And so we get 2,344. Yeah. Question.
So we're taking the proportion from Ames as 0.8. Would that not be the training data directly since we're taking 80%? So we're taking Ames split and further dividing it with the training data.
No, yeah. So the original Ames data is 2,930. Okay. And right now I'm saying I want about 80%, okay? So I think 80% of 2930, so 2930 times 0.8 is 2,344, and indeed, that's what it has done. Now, it's just, you get back this, so this is the original Ames data, and then we run this initial split, and all it does is it has basically like shuffled the rows, and all it has done is this. Okay, it's just basically just labeled some of the rows to be train and test. Okay, but I can't do anything with this just yet. Okay, and so if I want this part right here, I call, I forget, training? It's training, yeah, okay? I call training, oh, sorry, this is now called Ames split, okay? I call training on Ames split, and that's gonna be this row with 2,344, okay? And then this part over here, this is what I get when I do testing on Ames split. Okay, and that's going to be this with 586, is it? Okay, 586. So it's not, we aren't further splitting this right now, okay? So this is our initial split. And all we're doing is we're just kind of like labeling some of these rows to be training and some to be testing. Here, it's not going to be like the top are 2,000 are the train. It shuffles them all up. Okay. Yeah. So that's what we get, and we can check. Yeah, the training Ames training will do that. Okay. Blah blah blah. Okay. So I just copied this directly. There's a few things, and one of them, and this is actually almost always recommended, is to stratify, to use stratified sampling when you split your data. Okay, so when you split your data, we almost always recommend stratifying things. So, for example, especially if you're doing like a classification problem, and if there's a class imbalance. So, for example, let's, a common data set is like predicting credit worthiness and loan defaults. So if you're a bank, okay, you want to lend money to people and charge them interest for lending money because that's how you're going to make money. That's how you earn your profit and stuff as a bank. Okay, but when you lend people money, you also run the risk that they don't pay you back, right? So if you give a friend some money, you're expecting them to pay you back, maybe. But if they don't, then you're out of that money, right? And if you're a bank, somebody doesn't pay you back, that's a problem. You lose that money. And so you want to evaluate, okay, can I trust this person to pay me back? And the vast majority of people pay back their loans, okay? But maybe around 2%, something around there, might default, okay? Might not pay money back, and or something like that. And so you want to evaluate that. And so you might have this big data set, okay, of like thousands of people, and only a small percentage default on their loans and don't pay the money back, okay? And if you just do this random process here, okay, just kind of by random luck, in your training set, you might end up getting like 3% don't pay back. In the testing set, only 1% don't, default. And so now your model is going to, predict things incorrectly, all right? And so you kind of want to ensure that in your training it's 2% and in your testing it's 2%, okay? And so you use stratified sampling to kind of ensure it says, hey, look at this variable, look at the output variable of like whether they defaulted or not, and use that as far as splitting the training and the testing, okay? You can also do this for a numeric variable. So for a numeric variable, they stratify using like quartiles, and they'll say, here we're going to look at this numeric variable. This is like the cutoff for the top 25%. This is the cutoff for the next 25%, the next quartile, and the next quartile. And they'll kind of ensure that in your training set, a quarter of your data is from the top, a quarter of the data is from the next group, and a quarter of the data is from the next, and the quarter is at the bottom, okay? And it's going to ensure that the testing data also kind of follows that distribution. And so that's going to help make sure your training data and your testing data at least look kind of similar. Of course, there's always going to be a random aspect to it, and it's not going to be perfect. Same kind of thing plays out in the Kaggle competitions. High-performing models are going to perform well, but there's also a little bit of random luck in terms of like, does the test data look like the training data, and things like that. So for regression problems, the outcome data can be binned into quartiles and then stratified that way. Okay. And so if you want to do that, you can do that by just specifying strata in the initial split. So here I'm going to just run kind of the same thing. We do initial split on Ames, and I'm going to say stratify on sale price. Okay, and then once we do that, we get our training and our testing split. And this just ever so slightly adjusts it to 2342. Okay, and I guess this would be 588 then. All right. There's another case for like time series data. Okay, so if you're dealing with time series data, you don't want to just randomly select. Okay, so most time, if it's not time series, you want to like randomly select your rows. But for time series, it's always kind of like, let's say you have data from January through August. Okay. You want to your training wants to probably be from like January through June, and then you'll test on July and August or something like that, right? So it's always kind of like, because you want to be able to ask like, how well can I predict like what's coming next? Okay, so based on like this historical trends and stuff, like can I predict, so maybe you have 10 years of data, your training should be like the first 9, and then can I predict the 10th year? And if I can predict the 10th year pretty well, we're hoping we can predict the 11th year well too. Okay, so time series, you'll kind of hold out basically, then you kind of keep things in order, and then if you're doing an 80-20% split, you'll keep the last 20%, the most recent 20% in your time series out for your training set. Okay. So anyway, this would be the initial split where you have the training and the testing data, and again, this test data gets used. This is like the final exam, and you want to kind of keep this held out, right? But now this is our actual training data, right? And we want to kind of test ourselves, all right? So you have like, someone gives you the set of practice questions, practice exam questions, and if you want to test yourself and see if you've learned them, you actually might want to only use some of those during your study process, and then you might want to do like a little self-test, okay, with some of the remaining questions. And so we are going to further split this data into what we call brain just stopped. Oh, okay. An assessment and a validation. Okay. No. Yeah. No. I'm sorry. Analysis. No. It's analysis analysis and validation, or analysis and assessment. Okay, validation or analysis and assessment. So we further split the training data available to us into more smaller groups there. Okay, so that's when we bring in cross-validation. Okay, so cross-validation is going to take this training data and further split it, okay, into our analysis set and our validation set, maybe also called the assessment set. Okay, and so this training and the analysis and the validation set are further used to kind of test our performance without looking at the final test data set. Okay, so we use the analysis set to fit a model, then we validate the analysis set against our kind of validation or assessment set. Okay, and we kind of get a preview score before we get to the final testing set. Okay, and so this diagram comes from the ISLR, this textbook over here, and then I also have diagrams coming from resampling for model performance here. Okay, so here's this is kind of the diagram here. So this is all of our data. The initial split does this. We have our training and we have our testing. And then within our training, we further split it into analysis and assessment sets. And we do this, we have different resamples or something like that, okay? So here, this is just one possible way, and this is kind of like doing a 50-50 analysis validation set, right? It just takes the original data, it shuffles them. That's what here the 72213 is supposed to symbolize the fact that they shuffled the observations, okay? And they put those into kind of your training or your analysis set. The remaining observations go in the validation set, okay? And we do that, okay? And so the textbook, Introduction to Statistical Learning with R, ISLR, uses this auto data set, and they want to learn about the relationship between gas mileage, MPG, and the horsepower. And generally, in general, if a car has more horsepower, it gets not as good gas mileage. And it says, all right, let's just try fitting out different relationships. We can try fitting a straight line linear model. We could try fitting a quadratic model. We could try fitting a cubic, fourth degree polynomial, fifth degree, things like that. And we can see, how does that affect the the performance on the training data, okay? So we're going to measure training error. And, this is just basically like if you're using R squared or residual sum of squares, basically the more complex your model gets, you can always eke out a little bit more performance, right? You can always gain some R squared value. You can always kind of reduce your RSS, okay? But we know that we also run the risk of overfitting, okay? And so what we do is, this is how the validation set, okay, how the mean squared error on the validation set changes as our performance, as our polynomial gets more and more complex, okay? So when we fit just a linear model, the error on the validation set is high, okay? And then as we fit a quadratic, it goes down. And as the degree of the polynomial goes up, gets higher and higher, we see our performance kind of stays flat, okay? Whereas on the training data, I don't have it plotted here, but with the training data, the relationship's gonna look like this, okay? where it's going to just kind of keep getting better and better and better. As it gets, this is more complex, it always kind of goes down. And it might kind of flatten out where the amount of error, but as the model gets more and more complicated, you can always kind of get your R squared value just a tiny bit higher, right? And that's why we say, looking at R squared only is not the best plan because you're going to overfit your thing. And so when we look at the validation set, we see, okay, it's not always improving. Actually, going from a second degree polynomial to a third degree polynomial, it goes up a little bit, right? The amount of error in our validation set goes up a tiny bit, okay? So that's what this plot is. It says, hey, if this is how you've split it on your training and your validation set and you run it, when you go from the second to third degree polynomial, your error goes up a little bit. Third to fourth degree, it kind of stays flat. Fourth to fifth, it goes down, and so on and so forth. Okay, what is this thing on the right? Okay, well, we said, what would happen if I just did a different random training or analysis and validation set? So if I redid this process, but I just shuffled my observations and I got a different analysis set and I got a different validation set, okay? What happens is you get a similar trend, but you get different results, okay? So depending on what validation set you have, okay, you might get one of these different lines, okay? And so this line, we started off here with the linear, and then when we go down to the second degree polynomial, it goes like this. Going up to a third degree polynomial, our error goes up. And then fourth degree, it goes up again. Fifth degree, it goes down. Sixth degree, it goes down. Seventh, or eighth degree, or ninth degree goes up, and so on. Like you get this kind of line, right? Here's like this one in like bright yellow at the bottom. It looks like going from second to third to fourth, like it all kind of goes down, reaches a minimum at seventh. And so basically, depending on your just how the data got randomly shuffled into your analysis set and your validation set, you might get like a different kind of path as far as how much mean squared error you have when you test your performance. Okay, we see similar trends. Linear does bad, and there's a huge drop going from degree 1 to degree 2, and then similar trends of like things don't seem to improve that much. But you can see the individual lines, like they vary quite a bit. Okay, so that's what we're seeing here. Okay, that's what this plot is. So this is just one particular split of the data, and these are just different possible random splits. Okay, so the drawbacks of using only one validation set is that you don't know. All right, is yours this one up here? Is it this one? Like, you usually just have if you just have one validation set, you don't know like which of these things you have. Okay, we're hoping the one you have is reflective of the overall thing, but maybe or maybe not, right? So the estimate of the test error can be highly variable depending on the points selected to be in the validation set. Only the observations of the training data are used to fit in the model, and the observations of the validation set aren't used. And so, your performance of having only one validation set, not great, okay? So just doing kind of this one split between analysis and validation is on one end. And on the other end, you have, on the other extreme, you have leave one out cross-validation. And leave one out cross-validation says when you split it into your analysis and your validation set, use all of your observations except for one to be in the analysis set. And then the validation set is going to just be the one observation you left out. Okay? It's kind of like you're going to, like, it's like having one question on the final exam. Okay? And so You use everything except for one observation, okay, and you use that to kind of train, and then you use that one observation to in the validation, okay? But you do this n times. So if you have 1,000 observations, you're going to do this 1,000 times. Every single time, 999 observations in the analysis set. And then you validate against that one observation. But you do this 1,000 times, and all 1,000 observations has a turn at being the one kind of evaluation question, okay? Or the evaluation or the validation observation. So only one observation is used in the validation set, okay? But we fit it n times. We do this n times, and every observation has a turn at being basically the validation observation, okay? And then you take them average, okay? You average all of these different mean squared error values, okay? And so this is kind of the diagram. Here, observation 1 is your validation set, and you train or fit on everything else. In the second run, observation 2 is your validation set, and you train on everything else. Observation 3 is your validation set, you train on everything else. And your MSE is just the difference between, for the first run, is what was the actual value of y1 compared to what was your prediction for y1, okay? Square it, okay? You do it the second time, what was your actual value for observation 2 compared to the predicted value for observation 2. And you do this again and again, okay? This is not recommended, okay? There are some advantages, and there are some things. There's like no randomness at play when you do leave one out cross-validation. You don't have to worry about like randomly, like depending on how the thing was randomly shuffled, like are you going to get something wildly different? That doesn't happen with leave one out cross-validation because there's no randomness, right? Every observation has a chance at being the validation set, okay? But basically, it's a little bit overkill, okay? It's very computationally expensive, especially if you have a very big data set. So you have 3,000 observations, you have to fit a model 3,000 times, okay? Which is a lot, but your computer can handle it probably. But if you have like 3 million observations and you have to fit the thing 3 million times, that's a waste of computational power, okay? It's a waste of, clock cycles on your computer, and so you don't want to do that, okay? And also like statistical properties of it also not super great. So we don't really want to do leave one out cross-validation, okay? So instead, we do k-fold cross-validation, okay? K-fold cross-validation says, hey, we're not going to do one observation at a time in our validation set. We're going to just kind of take maybe 10% of our data, okay? So we'll split the training data into like a 90-10, okay? Maybe 80-20, okay? And so we are going to split the data into k different groups or folds, and then each fold, okay, each kind of sub-partition gets a chance or gets a turn at being your validation set, okay? And then you calculate the MSE on the validation set. You repeat this k times, okay? And then you take the average, all right? So you're gonna overall do this. So common choices are like 5-fold cross-validation or 10-fold cross-validation, and that's what we have. In the Tidy Models package, it's called V-fold cross-validation. I don't know, they use a different letter, but it's the same thing. Okay, K-fold cross-validation, V-fold cross-validation. I don't know, just using different letter name for the concept here. Okay, what's the effect of using a big V or a small v or a large? So larger values result in resampling estimates with small bias but substantial variance. Smaller values of V have larger bias but lower variance. Okay, and the default in tidy models is 10-fold cross-validation, but you can use whatever number you want. But 10 seems to be a different decent choice. Okay, this is kind of the diagram for 5-fold cross-validation. About 20% is represented in orange, and we use 80%. We train on the 80%. We assess or validate on the remaining 20%, and then the first time the first 20%, then the next 20%, then the next 20%, so on and so forth. Okay, and that's what we have here. Okay, there's and so when you do say like 10-fold cross-validation, this is kind of the result that we get. So if you just show, so this is, on the left is leave one out cross-validation, okay? There's no randomness, and this just shows the performance of going from, linear to quadratic to third degree, fourth degree, fifth degree polynomial, and so on and so forth. And leave one out cross-validation, there's no randomness at play, okay? With 10-fold cross-validation, these are the results of the 10 different folds, okay? And you can see there's 10 different lines here, but they're all kind of very, very close to each other. So there's a little bit of variation between them, okay? A little bit of variation between them, but overall, they align very, very similarly, okay? So that's a big improvement over back here, where we just had one random thing. They varied quite a bit, okay? So with 10-fold cross-validation, we do have a little bit of variance, but overall performing quite a bit well, okay? There's a nice diagram in the Tidy Models textbook, okay? So here is, if our full data set has 30 observations, let's say we do 3-fold cross-validation, okay? In 3-fold cross-validation, it splits the data randomly into 3 groups of 10, okay? We have green circles, yellow squares, and blue pentagons, okay? And when we do cross-validation, okay, we're going to repeat the process 3 times, because this is 3-fold cross-validation. So the first time we fit our model to the yellow squares and blue pentagons, and we test on the 10 green circles. Okay, and then the second time we fit on the green circles and blue pentagons, and we test on the yellow squares. And then the third time we fit to the yellow squares and green circles, and we test on the blue pentagons. Okay, and so for each fold, 1/3 of the data is in our evaluation, our validation set, okay, and then the other 2/3 are in our training set. And so this is kind of a nice diagram of how kind of V-fold cross-validation works with 3-fold cross-validation. And you can just kind of imagine the same kind of thing with 10-fold cross-validation, where we train on 90%. And we test on the remaining 10%. Okay. So leave one out cross-validation is actually just a special case of k-fold cross-validation where k is equal to n. It's just that's kind of excessive, right? And so fitting only say 10 different folds or something is going to save us a lot of compute power. Okay, and so, we can use cross-validation because it can estimate the mean squared error of the test data. So even though we haven't actually seen the test data, by getting a sense of what kind of MSE we get on our cross-validation performance, that'll give us an idea of what our MSE will be on the unseen test data. And then also, it will help us figure out which is the best model to use, right? So we can help decide, do I want to use this kind of model or another kind of model, because these models seem to perform best. The quadratic model seems to perform best when I do k-fold cross-validation or something along that, okay? Now, this first effort of using cross-validation to estimate the mean squared error of the test data is actually kind of tricky. Okay, so using cross-validation to estimate the test mean squared error is tricky because we don't know exactly how much mean squared error there is in the test data because we don't know the actual exact model that exists in the population. So we can kind of try to figure this out by using simulations. Okay, and so if you're running a simulation, then you know exactly the different properties here, and you know exactly how much mean squared error there should be, and so we can revisit kind of some of the models that were created in one of the earlier chapters, and we can discuss like the trade-off between model flexibility and the resulting mean squared error. And, you know, we talked about fitting like different smoothing splines with different levels of flexibility. Like we fit like the blue thing and the squiggly green line and things like that. And then also just a linear model and things like that. And so with cross-validation, you know, when we were, so if I pull up my slides from, I guess, Tuesday, you know, we were... I was able to like make up, you know, show you these pictures where we could say like, oh, this is what the mean squared error looks like on our training data, and this is what it looks like in our test data. Okay, and the test data, like we could generate these plots because these were simulated data sets where I knew exactly what the training, what the true relationship in the population looked like, so I could generate new random data sets and figure this curve out exactly. Okay. In real life, we don't have that, okay? With cross-validation, we're just dealing with this. We don't have this yet, okay? We don't have the test set, okay? So we're just kind of, we're guessing this. We're using this to kind of try to guess what it is in the test data, which, you know, has its limitations, okay? So this was, this is the curve that shows the true relationship over here in the black line, and because we know the true relationship, we are able to get the exact test mean squared error. Okay, but again, that's only possible because it's a simulated data set. Okay, so these are like the different plots that we have. We got this model and this model and this model. Okay, and so these plots over here with the red line, this is the test MSE that we know because it's a simulated data set, okay? Over here on these plots, okay, so the blue line here is the test mean squared error, okay? So if I go back to the previous slide, so if you look at this curve, this red curve here, that matches this blue curve right here, okay? And if you look at this red curve right here, that matches this blue curve right here. And then if you look at this red curve here, that matches the blue curve on these plots, okay? And so these are the blue curves here represent the true test mean squared error that we can know because we've simulated the data, okay? Again, in real life, we don't have this luxury. In real life, we're not simulating data, we're like using real data. And so the hope is that cross-validation is gonna give us a sense of like the best performing model, right? Okay, and so that's what these, the orange lines, okay, show, and also the dotted black line is from leave one out cross-validation. So using the orange, so when you do cross-validation, okay, and you do something and you fit, you know, you're fitting different models of different flexibility, when you do cross-validation using like tenfold cross-validation, it says the best fitting model has this level flexibility, okay? Whereas when we knew the true relationship, the one that minimizes the test MSE had a flexibility, flexibility level 5. And when we do cross-validation, we get flexibility level, 8. Okay, so it's a little bit off, right? Sometimes it's more off than others. So here, and this curve is quite a bit different from the test MSE. So this is our estimated mean squared error based on cross-validation, because we don't have the actual test data available to us, okay? Here it is for this relationship, or the true kind of test MSE curve looks like this. And, we get some similar shape, but here it says, the best model is over here, and when we do cross-validation, we get something a little bit off, okay? And here, it seems to perform decently well, okay, where cross-validation aligns with the actual things quite well, okay? So all of this to show that cross-validation has its limitations, okay? It's probably our best tool that we have because we never actually get to see the test data until it actually is test time, okay? So we don't actually know what the test MSE is going to be, right, until test time. But as far as like what's available to us, cross-validation probably is our best tool that we have, but it's limited, and that's because your training set doesn't look exactly like the test set, and you're trying to figure something out based on something you don't have, okay? So yeah, limitations. Using cross-validation, so again, there's mismatch in the curves. There's going to be mismatch in terms of exactly what's the best fitting model. It's not going to be perfect, okay? We do see that there is like a decent amount of lineup, but again, it's not going to be perfect, right? So when you use cross-validation, it's going to say, hey, we think this is the best model. And when you actually look at the actual test data set, maybe it was off a little bit, okay? So, looking at this, here it said the best model is going to be right here. And so according to cross-validation, you're going to end up like right here, which, is a tiny bit higher than, a little bit different, okay? So the true best model was down over here. We selected model here, but how much of what's the vertical difference between this location and this location in the test MSE? Only a little bit, right? Similarly, what's the vertical difference here? Not a ton. Here it's like practically nothing, okay? So, how complex of a model should you pick? Cross-validation says you should pick a model that's this complicated, which is, a little bit more higher than, than what it actually is. But the vertical difference in like the test MSE, very little. So it's actually doing a decent job, I would say, okay? So it is our best tool. Again, not perfect. Tidy Models makes this process of doing like V-fold cross-validation quite a bit easy. And so here I'm jumping ahead to chapter 10, where we're doing cross-validation here, okay? So again, we have the initial split, and then once you have the training data, then we do cross-validation. And that's what we have here. And so you can do V-fold cross-validation by running this command vfold underscore CV. Vfold underscore CV. So you take this training data, right? So with this training data, now we run vfold CV, and this is going to kind of create this like folded up version, okay? Folded version of the training data, okay? And it says these are all of the different folds where the training data has 2,342 observations, and you can see it has split all of them into kind of the 2,342. So we did we did stratified sampling, so that's why it's slightly different. But if I do 2107 plus 235 here, that's the 2,342. So when we take this, and it's going to say we're going to analyze on 2,107, and we're going to do the validation against these 235. Okay, and on the second fold, we're going to analyze on these 2,107, and we're going to validate on these 235. For the third fold, we're going to analyze on 2,108 and validate on 234. Okay, just because with 2,342, if I divide by 10, okay, some of them are going to have 234 observations, and then some of them will have 235 observations. Okay, so that's what we have. So this is going to be 10-fold cross-validation. Here it only shows the first, I guess, 6 or 7 folds, but there's 10 of them. Okay, and this has all of those different splits. And if you want, you can extract, you can extract the actual 2,107 observations, and you can extract the actual 235 observations. That is available to you if you really wanted to do that. You can do Ames_folds $splits, and it will say, all right, this is kind of the data set here, 2,107 and 235 observations. And then if you take that and then you say, I want the analysis, right? I want those 2,107 observations, okay? You can get those 2,107 observations, right? And you'll get that actual data set. Now, do you actually want to do that? With tidy models, you don't need to. You don't need to, okay? I guess, back in the day, if you wanted to do cross-validation, you would have to write a script that does actually extract out these observations, you fit the model, and then you test it on the remaining observations, okay? But with tidy models, it does all of this for you in the background. It just kind of creates these data structures, and then you say, hey, fit the model and do it automatically and do the k-fold cross-validation. And it will automatically fit the data to the 2,107 evaluated on the 235. And then it will automatically do it to the next set and evaluate, and the next set and evaluate. And it will do this all for you kind of in this streamlined fashion. Now, again, if you want to kind of verify everything yourself and you say, I want to see those actual 2,107 observations myself, yes, you have that option, and you can extract out the analysis data set. I mean, this is basically what the computer is doing for you in the background. It is extracting out these data sets and fitting it on this data set, and then evaluating it against the assessment set, right? I want to see those 235 observations that I'm assessing on. It is doing that for you in the background. You can see it yourself. You can do it, but you don't have to. It really kind of saves a lot of work for you, which is wonderful. Okay, and so package tune allows you to kind of interact with these folds without having to do this directly. Again, this option to work with these things themselves, it is available to you. You don't have to, only if you're like if you want to peek under the hood, you can, right? But you don't have to, okay? And you can do that. Okay, so one issue with cross-validation, however, is that there is variance, right? So if I do 10-fold cross-validation, right, I have, these are like my folds. And if you do 10-fold cross-validation on the exact same data, your 10 folds are going to be different, right? It's like taking a deck of cards and I deal out 10 piles of 5, and you deal out 10 piles of 5, our piles are going to be different, okay? And because our piles are different, our results are going to be different, okay? So if you have the computational power and the luxury to do this, you can repeat the process again, right? So this is called repeated, okay, cross-validation. And it's recommended if you have the time and computational power. So depending on your model, it might take like an hour to do it once, and then you don't want to repeat it 5 times because then it'll take 5 hours to do it. So, if you have a really complex model, maybe you don't want to do this, okay? But if you have a simple model that takes just a couple minutes and you say, hey, let's go ahead and try run it 5 times just to kind of make sure our performance is good, okay? Because that's our secret is like we want to make sure it's running well by just repeating it again and again. So you can do v-fold cross-validation, and you say, hey, I want 10 folds, v is equal to 10, and I want to do repeats equal 5, okay? And then so you will have basically a total of 10 folds 5 times, so I guess 50 folds, okay? So you're going to have repeat 1, and you'll have fold 1 through 10, and you'll have repeat 2, folds 1 through 10, and repeat 3, folds 1 through 10, and so on and so forth, okay? And again, this is all automated for you with tidy models, okay? And so we have that, okay. What else do we have? If you look at some of these, again, I'm not going to test you on anything really, but you can keep, so this is all red here, and so you can see as you do more and more of these replicates, 10-fold cross-validation, and as you do it more and more, then your standard error goes down as you might. All right, so you have other kinds of validation methods. So you have Monte Carlo cross-validation, and these are all things you can do. Let me see. Is there anything else? Bootstrapping. Yeah, okay. Well, so other things exist. You can read up on the textbook about them. You can probably find YouTube tutorials about them, but yeah, don't worry about it. Okay. So I guess in our next lecture, we will start talking about, okay, once we have this cross-validation set up, then the way we use it is by fitting our model and evaluating our performance, okay? And that process is going to be automated through the fit resamples function, okay? And so we'll, I've mentioned, some of these packages that exist at the top with like workflows and fitting things, and so Tidy Models is going to kind of automate all of this stuff for us, and we'll take a look. All right, I want to encourage you to just kind of make sure you start reading some of the textbook, Tidy Modeling with R, and then also the corresponding chapters from Introduction to Statistical Learning with R. Okay. We'll wrap things up here. Have a great rest of your day. No office hours today. I'm going to be on an airplane, and then, but I'll check in online tomorrow and on Saturday, and I can see you guys then. All right. Have a great week, and we'll see you Tuesday.